Hello, George Romanic here. Today we are going to explore effusion and gas leaks of an ideal gas through very small opening into vacuum. This theory is very important, and we will use kinetic theory of gases to describe this process. The importance of theory is mainly twofold, at least from my point of view. One, we will use some of the findings in today's video to explore diffusion of gas, which is of enormous importance in atmospheric sciences and engineering. And secondly, this theory played important historical significance for the development of kinetic theory of gases, as you will see in today's video. Gas leaks are very important, and many of them can be described using kinetic theory of gases. There are certain types of gas leaks. If you have those, you should probably see your doctor, and perhaps kinetic theory of gases is not the first option you should seek. Let's explore effusion. Our discussion of effusion starts by looking at the following situation. We have a box, and that box is filled with an ideal gas. This ideal gas has temperature T and pressure P. Atoms or molecules in this gas are moving in any given direction, and they are in thermal equilibrium. Temperature, namely, is not changing with time. This box, as you can see, has a hole, a small opening, and a gas can leak through this hole. Here we have to be a little bit specific. What do we mean by small hole or small opening? Well, we mean that the diameter of this hole is smaller than the mean free path of these atoms. And of course, you will remember from my previous videos that the mean free path is average distance a molecule or atom travels between two collisions. As I said, the gas will start leaking through this hole. For example, this atom is going towards the hole, so it will eventually escape this box. Effusion is escaping of a gas from higher pressure into lower pressure. So we will assume that outside of the box we have low pressure. Ideally, it is a vacuum. So how do we determine the rate of effusion, which is the rate of escaping of these molecules from the box? Well, we will take knowledge from one of my previous videos where we investigated the collision frequency between molecules and a wall. You will remember that in that video we determined that collision frequency, CF, between atoms and a wall was P, which is pressure in the gas, divided by the square root of 2 pi mkt, where T is absolute temperature of the gas, K is Boltzmann constant, 1.38 times 10 to power negative 23 joules per Kelvin, and m is mass of a molecule. Now you will kindly remember that this expression was derived for unit area and unit time. Now, how do we modify this to account for collisions with this hole and not unit area? Because hole is not unit area necessarily. Well, we do it as always. We say that collision frequency with the hole is collision frequency per unit area times the area of the hole. This small a is the area of the hole. Very well. Now let us say that n is total number of particles in the box. Then, of course, dn dt will be effusion rate. Where t is time, of course. Or, combining this with that, we can see that dn dt will be cf times a, but with a negative sign. Why negative sign over here? Well, because as the gas is escaping this box, the number of atoms in the box is decreasing. So n will decrease with time. Well, this is further equal negative. I plug in this expression over here. P times this A divided by square root 2 pi mkt. Now, this formula has an important historical significance. It was in 1829 that Thomas Graham experimentally demonstrated that the rate of effusion, namely dN dt, is proportional to 1 divided by square root of mass. So in 1829, Thomas Graham demonstrated this experimentally, and you will remember that this year is before the theoretical discovery of kinetic theory of gases. So he experimentally did this just like Boyle, Gay-Lussac, and other people discovered many things about gases before we knew about kinetic theory of gases. So how did Graham discover this? Well, he had a nice flask that maybe looked something like this, I don't know now. And here he had a very good plug. Here he had a tube that was leading to vacuum. Then through this plug he would insert a syringe like so. And this syringe was filled with a gas, 25 milliliter of gas. Then he would use a stopwatch to measure time required for this gas in syringe to escape through this needle, through the end of the syringe. And what he concluded from this experiment is that the rate of infusion dN dt is proportional to 1 divided by square root of density. But that is, of course, the same as 1 over square root of mass, because volume in this experiment, of course, is constant. Today, this relationship is known as Graham's law of effusion. Basically, what Graham discovered here is that at same temperature, lighter atoms, such as, for example, hydrogen or helium, move faster than relatively heavy atoms, such as, for example, carbon dioxide or SO2 and so on, because he performed this experiment for different gases. Later, the great and powerful Maxwell derived this theoretically, and we saw that in my video on the temperature of the gas. Namely, if temperature is constant, lighter atoms have to move faster than the heavier atoms to preserve temperature equilibrium. And this is exactly what Graham discovered here experimentally. Now, going back to our formula and our experimental setup, notice that as the gas is escaping this box, pressure in the box will decrease. And we can find this decrease of pressure using the equation of state. Namely, we know that PV is equal nKT, where V is volume of this box. Or, from here, we have that P is equal nKT divided by V. Now I differentiate this with respect to time, and I will get the dP dt is equal K T capital N here, divided by V dN dt, because remember, temperature is constant. We are keeping this gas at constant temperature and volume of the box is constant, so these constants end up in front of differentiation. Or inserting our expression for d and dt from above, we can get that dp dt is equal negative kt over v pa over square root 2 pi m kt. Or from here it follows that dp over p is equal negative square root kt, when I combine this and this, over 2 pi m times a divided by v, this a, this v, and dt. Now this whole thing is a constant, and I will call that constant 1 over tau, which means that tau is equal square root 2 pi m divided by kt times v and divided by a, where a is area of the hole. And notice that this constant has units of second, which means 1 over t is 1 over second, and that will cancel with this second over here, so this ends up being non-dimensional quantity, as well as this is non-dimensional, so our dimensions are good. So one can write, therefore, that dp dt is equal dt negative dt over tau, or integral of dp over p, or integral dp over p is equal negative 1 over tau dt. Well, at the beginning, time t equals 0, pressure in this box was some original pressure that we assume we know, and that is P0. And then at time t, there is some pressure P in the box. Therefore, solution of this integral is ln P over P naught is equal negative t over tau, or after we pass with exponential function through this expression, we will get that P is equal P naught e to negative t over tau. And this is the rate of effusion with respect to the change of pressure of the gas in the box. This tau that I define here is known as the time constant. Notice that when t is equal tau, when I set up here t equal tau, then p will be equal p0 e to negative 1. And that is approximately 0.37 P0. Which means when t is equal tau, pressure of the gas in the box is 37% of the original pressure of the gas in that box. This formula also has very important historical significance. It was used to find molecular mass of different molecules. How was that achieved? Well, we can measure pressure easily. We can measure initial pressure in the box. We can measure time, and in this tau, we can measure temperature, volume, and opening of the hole easily. Because we can measure all these things, the only unknown is mass, and therefore we can calculate mass of molecules that are escaping through the box. Similarly, this formula was also used to determine vapor pressure of different substances. If we put a substance in a box, let's put it like this, there is a box over here, and I put some substance over here that is sublimated. And here we introduce a small opening in this box, and the gas starts escaping. Well, in this setup, we can measure the temperature of the gas. We know the volume of the box, we know the size of the opening over here, and therefore we also know, by the way, mass of molecules that are sublimating. So the only thing that is unknown is this pressure, but then we can calculate that pressure by knowing all other quantities. And that's how people use this equation to find vapor pressure of different substances. The beauties of kinetic theory of gases once again show themselves. This video that describes effusion and gas leaks is very important for our understanding of behavior of an ideal gas in idealized situations. Until next video, goodbye.